Good afternoon. My name is Satveer Singh, Assistant Professor, Department of Mechanical Engineering, IIMT College of Engineering within Noida. Today, I am giving a lecture on boundary layer thickness. So we start from the topic one by one. What are how the layer formation, how is the boundary layer thickness work, and what are the different thickness, energy thickness, and momentum thickness. So we are starting from the initial boundary layer condition. So first of all, we have to know about what is boundary layer. So starting from the initial point, that is the boundary layer. So what is boundary layer? So we can say that when a real fluid flows past a solid or the solid wall, the fluid particles adhere to the boundary and the condition of no slip occurs. Basically, there are if we talk about the two types of fluid, that is one is ideal fluid, other one is real fluid. Ideal fluid is that fluid which have no viscosity, no surface tension, and no compressibility. But in case of real fluid, it has basically the viscosity, surface tension, etc. But there is no uh, real this type of fluid basically occurs. So if we talk about when a real fluid passes a solid body or the solid wall, fluid particles adhere to the boundary and the condition of no slip occurs. This means that the velocity of fluid close to the boundary will be same as that of the boundary. And if the boundary is stationary, the velocity of fluid at the boundary will be zero. It means that when the boundary is stationary, means that in a static condition, then velocity of fluid particle at the boundary should be zero. So the velocity, we can say that velocity will be higher, and as a result of the variation of velocity, the velocity gradient, that is du upon dy, du is the change in velocity and dy is the fluid thickness, will exist. Basically, the velocity of the fluid increases from zero velocity on the stationary boundary to the free stream velocity, that is denoted by capital U, of the fluid in the direction normal to the boundary. This variation of the velocity from zero to free stream in the direction normal to the boundary takes place in a narrow region in the vicinity of solid boundary. So we can say that this narrow regions of the fluid is called the boundary layer, and the theory dealing with the boundary layer flows is called the boundary layer theory. So if we talk about the boundary layer theory, then we will discuss the next point, that is the according to the boundary layer theory, the flow of the fluid, you can say that the flow of the fluid in the neighborhood of the solid boundary may be divided into two regions. So suppose this is the solid body, and basically we are going to flow liquid on this boundary or this solid surface. Then if imaginary boundary has been formed, that is called boundary layer, and this is called the u is the free stream velocity, that is the directly the velocity of flow that is directly in contact with the solid surface. So we can say that a very thin layer of the fluid called the boundary layer in the immediate neighborhood of the solid boundary, where the variation of the velocity from zero at the solid surface to the free stream velocity in the direction normal to the boundary takes place. So there will be a velocity gradient, that is du upon dy exists, and fluid exerts a shear force, or you can say that fluid exerts a shear stress on the wall in the direction of motion. So according to Newton's law of viscosity, tau is equal to mu du over dy, as we know very well, and in which that is tau is the shear stress and mu is the coefficient of viscosity, or you can say that coefficient of dynamic viscosity, and du is the change in velocity, and while dy is the fluid thickness, and du upon dy whole is called the velocity gradient. Next we will talk, that is the what is laminar boundary layer. So what do you understand by laminar boundary layer? So suppose for defining the boundary layer, or that is the laminar boundary layer or the turbulent boundary layer, if we determine the laminar boundary layer or the turbulent boundary layer, we have to know the concept of the boundary layer formation. So consider the flow of fluid having free stream velocity over a smooth thin plate which is flat and placed parallel to the direction of free stream velocity. Suppose This is a plate, and this plate there is two ends, that is end A and end D. And A is called leading edge, and D is called the trailing edge. And if we flow the liquid on this plate, then this type of figure can be exist. So in this case, we have divided this plate into the three regions. First that is region is A E B, or and the second region is E B C F. Third region is F C D G. So there are three regions formation. So we can say that this A to E shows the laminar boundary layer in which laminar flow takes place, and the EF shows the transition boundary layer, and FG indicate the turbulent boundary layer. And we can see a laminar sublayer in the region FCDG. Basically, this laminar sublayer is adjacent to the surface of the, that is solid surface, and it is found in turbulent zone. So this is a very thin layer, and here the velocity variation takes place. We can discuss this in detail in the next uh, slide. So we can say that there are the velocity of the fluid on the surface of the plate should be equal to the velocity of the plate. But plate is stationary, and hence velocity of the fluid on the surface of the plate is zero. So we can say that, uh, but it can be seen that but at a distance from the plate, fluid is having a certain velocity, and thus the velocity gradient is set up in the fluid near the fluid with the uniform velocity. And this velocity is sometimes retarded, and velocity goes down at the subsequent point downstream to the leading edge. There are two types of edge, that is, one is the leading edge and another is trailing edge. The boundary layer region increases because the retarded fluid is continuously retarded, and this means that the thickness of the boundary goes small. And the boundary layer, we can say that there are three types of boundary layer is formed here, that is laminar boundary layer, turbulent boundary layer, and transition boundary layer. So we can say that the distance of B from leading is obtained from the Reynolds number is equal to 5 into 10 to the power 5 for the plate. And we can say that the Reynolds number can be determined by the following equation, that is Rex is equal to Ux by nu. Basically, x is the distance from the leading edge, and x is the distance from the leading edge, and this is the x, and u is the distance, that is free stream velocity, this is u, and the next one is nu, that is the kinematic viscosity of the fluid. So this is the next slide. We can say that to find out the laminar boundary layer thickness, we have used the formula, and Reynolds number is ranging from, that is 5 into 10 to the power 5, and you can say that this nu is called the kinematic viscosity. And if we talk about what is the x is the distance from the leading edge, and capital U is the free stream velocity. Now we can discuss about the turbulent boundary layer. In case of turbulent boundary layer, that is there is the flow exists, that is turbulent flow, and velocity of flow of the fluid is very high. If the length of the plate is more than the distance x, suppose in the figure last we have seen that in equation, and equation 13.1, we can say that if the length of the plate is more than the distance x, then the thickness of the boundary layer goes on increasing in the downstream side. So then the laminar boundary layer becomes unstable, and motion of the fluid within it is disturbed and irregular, which leads to a transition from laminar to turbulent layer. This short length over which the boundary layer flow changes from laminar to turbulent, this is called the transition zone. Now we can say we have seen the figure. In figure, that is the distance BC. We have indicated in the figure. There are various reasons in the figure that we can say that the turbulent boundary layer, the transition boundary layer, and the laminar boundary layer are fixed, and in the figure we have discussed earlier. Now, what is laminar sublayer? So, to know the concept of laminar sublayer, that is, we have to know what is the turbulent boundary layer. So this is the reason in which the turbulent boundary layer zone, basically laminar sublayer found in the turbulent boundary layer zone adjacent to the solid surface of the plate, as we seen in the figure 13.2. In this zone, it can be seen that the velocity variation is influenced only by the viscous effect. So we can say that the velocity distribution would be parabolic nature, and we can obtain a parabolic curve in the laminar sublayer. But in a view of very small thickness, we can reasonably assume that velocity variation in the is basically found to be linear, and velocity gradient can considered to be constant. Suppose, as we know that there is a formula of that is Newton's law of viscosity, that is tau equal to mu du over dy. Now we have to find out the boundary shear stress. है ना? So tau naught is the shear stress as the boundary, and it is denoted about tau naught, and tau naught is equal to mu del u by del y at y equal to 0. And for the linear variation, del u upon del y is taken as u by y. So this formula is used for finding the shear stress. And if we talk about the boundary layer thickness, it is denoted by delta. Boundary layer thickness is defined as basically the distance from the boundary of the solid surface measured in y direction, where the velocity of the fluid is approximately equal to the 99% of the free stream velocity. So, for getting the boundary layer thickness, we have to know what are the initial consideration. Then we have seen that the thickness of the laminar boundary layer is denoted by delta LAM, and thickness of turbulent boundary layer is denoted by delta TUR, and delta dash indicate the thickness of the laminar sub layer. Okay, next we will move to the next slide, and now we have to know what is the displacement thickness. Basically, this is the main. This thickness is very important to find out the numerical problem based on this laminar boundary layer. So basically, in the figure, displacement thickness, we have seen that the displacement thickness is denoted by delta star. Basically, it is defined as the distance measured perpendicular to the solid surface. So this is the solid surface, and we have to measure perpendicular distance here. Okay, so it is defined as the distance measured perpendicular to the boundary of the solid surface, by which boundary should be displaced to compensate for the reduction in flow rate on account of boundary layer formation. So now we can see that it is denoted by delta star, and delta star is the basically the denotation. Yeah, we can denote the diffusion thickness by the delta star. U is basically the free stream velocity, and when the liquid is passed freely on the over the solid surface, then this type of flow profiles can be seen, and this region shows the velocity distribution pattern. This is the boundary layer formation. Now we have to know how to derive the boundary layer thickness or the displacement thickness. Here in this case, we have to find out the displacement thickness derivation. So for this, we have to know what are the initial consideration for the displacement thickness. Basically, we have to consider a fluid having a free stream velocity of u, and this fluid is passed over the solid surface. Then at a distance x, from the leading edge, we have placed the sections 1, 1. We have cut, or we have inlined a section 1, 1. The velocity of the fluid at B is 0, and at C lies on the boundary of the solid surface, that is taken as capital U. Distance BC is called the delta, and we have seen the section 1, 1. In section 1, 1, we have initialized the initial parameters. First one is the y. Y is called the distance of the elemental strip from the plate, and dy is the thickness of the elemental strip. U is the velocity of the fluid at the elemental strip, and V is the width of the plate. Basically, if we found out the area of the elemental strip, then basically the strip is rectangular, so area dA, small area, equal to B into dy, where B is nothing but only the width of the plate, and we have to find out the mass per second, or the mass flow rate through the elemental strip. So formula is m equal to rho into V. Then If we calculate the final formula, then rho into velocity into area of the elemental strips you can calculate. So rho is the density of the fluid particles. That is, in case this is the density of the fluid particle, density is taken as 1000 because that is the liquid is flowing is water. So velocity is u and dA is the area of the elemental strip. So dA can be written as b into dy. We can take equation number 1 here, and if we find out the mass of the fluid per second flowing through the elemental strip, then we can finalize the formula again. That is, this formula is rho u b into dy. Okay, so here the velocity u is taken as capital U because velocity is free stream velocity here. Now we can check what is the reduction in mass flow rate when the liquid is flowing through the elemental strip. So reduction in mass flow rate flowing through the elemental strip is equal to mass per second given by the equation second minus mass per second given by the equation first. Basically, mass per second, the formula is rho u b into dy as we discussed earlier, and that is mass per second in equation 1. We can calculate rho u b dy. Now you can take common rho b in the mu, that is u minus small u into dy you can obtain easily. Now to find the total reduction in the fluid through the BC section, we have to integrate the previous equation. Integrating the limit, initial limit is 0 and final limit is delta. Delta is the boundary layer thickness. So we have to integrate. Then we have to find that there is rho b is the constant parameters, and we have taken it out. And the final equation is there is total reduction equal to rho into b integration of 0 to delta capital U minus small u into dy. That is the third equation. Here this case the fluid is incompressible, so density is same for at different sections of the fluid sections of the particle. Here delta star is basically the displacement thickness, and we have to find out the displacement thickness. Then we have to check what are the loss of the mass of the fluid flowing per second at a distance delta star. So formula is rho v into area, rho into velocity into area. Then we have checked that area equal to b into delta star, because delta star is basically the vertical distance we have take to find out the residual thickness. So now the formula is coming, that is rho capital U del star into b. Finally, we can equate equation number third and fourth, so we can find out easily the delta star. Delta star we can obtain here, that is 0 to delta 1 minus u by capital U. In some books you can check the formula, then u star, u capital U is denoted as u infinity. So no problem, we can take delta star is basically the displacement thickness, and that formula is derived here, that is 0 to delta integration of 0 to delta and 1 minus mu u by capital U into dy. So this formula is used to calculate the displacement thickness. Now come to the next point, that is the momentum thickness. So how to find out the momentum thickness? So we have to check how to find out the momentum thickness here. So momentum thickness is nothing but it is defined as the distance measured perpendicular to the boundary of the solid plate by which the boundary should be compensated for the reduction in momentum. Momentum is nothing but quantity of motion in a body, and in mathematical concept, momentum P equal to the formula is P equal to m into v. So this is very well known by everyone. M is the mass and v is the velocity of flow. So now we have to check what is the momentum of the fluid here. Momentum equal to mass into velocity, and mass we have calculated rho u b dy into u. Momentum of this fluid in the absence of fluid boundary we have taken. Then momentum equal to mass into velocity. So that is the mass, and the u is the velocity. Loss of momentum through the elemental strip. So we have to subtract that is the momentum of this fluid to the momentum of the fluid in the absence of fluid boundary. So we can get the equation rho bu capital U minus small u into dy. Total loss of momentum we have taken, that is the formula coming here, the zero integration of 0 to delta rho bu capital U minus small u into dy. Now come to the derivation continued here, and we can take theta. Theta is nothing but only the distance by which the plate is displaced when the fluid is flowing with a constant velocity of u. So capital U velocity, and then loss of momentum per second we have to find out. Then the formula we can use the mass of the fluid through theta or theta distance and into the velocity. Basically, mass equal to formula is the rho area into velocity, and again is the velocity. Then you can get the velocity square. So rho theta b into u square is the loss of momentum per second at a particular distance. So by equating question number 13.4 and 13.3, we can check the value, and when calculate we can solve the value. Then we can initially get what is the formula generating, that is theta. Theta is nothing but only the momentum thickness, which is equal to integration of 0 to delta u by u in capital U into 1 minus u by capital U into dy. You can take u capital U as u infinity. In some books the capital U in place of capital U infinity you can see. Now next the thickness is the energy thickness. Energy thickness is denoted as delta double star, but delta star we can denote the distant thickness, but by theta we can denote the momentum thickness. So we have to know what is the initial notation of the various thicknesses. So we'll talk about the energy thickness. Energy thickness is defined as the distance measured perpendicular to the boundary of the solid surface by which the boundary should be compensated for the reduction in kinetic energy of the flowing fluid, and now it is noted by delta double star. So for continuing for the derivation of energy thickness, we have to formalize in a similar way. Suppose mass of the fluid flowing per second through the elemental strip of the fluid thickness dy at intersection y, we can calculate, that is del rho u b into dy. Rho is called the density, and dy is the fluid thickness, b is the width of the plate, and u is the initial velocity. Kinetic energy you can calculate, formalize kinetic energy half mv square, and kinetic energy is nothing but the only the energy possessed by the body due to its motion. So formula is half mv square. M is the mass, so you can put the value of mass, that is rho u b dy, and velocity is taken as u, and square is available, and then u square is coming to the picture. Kinetic energy of the fluid particle in the absence of the boundary, we can calculate. We replace small u to the capital U here, and if we find out the loss in kinetic energy, then we can subtract the first kinetic energy to the second kinetic energy available at the absence of the fluid particle boundary layer. Now we have to calculate the total loss of kinetic energy. Then we can integrate the previous equation, that is 0 to delta half rho u b and capital U square minus small u square. So that is rho u b is the, basically rho is the density and b is the width of the plate, and half is the constant value. So all constant values coming outside of the integration, then the formula equation form is the new equation. Now we consider, let delta double star is the distance by which the plate is displaced to compensate for the reduction in kinetic energy. Then we can check what is the loss of kinetic energy. Then formula is half mv square. M is, that is rho, the density, into area into velocity, and velocity is taken as that is u square is obtained. Now the final formula is given as, that is half rho ub delta star into u q. Delta double star is basically the energy thickness, and area equal to b into dy, that is thickness, and here dy is taken as delta double star. Then we can equate that two losses of kinetic energy, then we can get this equation. Now equating both two equations, we can calculate and symbolize this equation. we can get easily the energy thickness equation. This is the energy thickness equation in which the U by capital U and within bracket 1 minus U square by capital U square into dy. So this formula is used for finding out the energy thickness. So we have to know what is the formula and how to derive the formula. Now we'll move out the how to solve the problem related to the boundary layer thickness. So this type of problem is very important for active students, and it comes in the fluid mechanics. Basically, the subject taught in the third sem of B.Tech students uh, of AKTU. So we have to calculate how to solve the problem related to the thickness or the boundary layer thickness. Basically, there is a problem. Find out the distribution thickness, momentum thickness, and energy thickness for the velocity distribution pattern is given as U by capital U is equal to Y by delta, where U is the velocity and Y is the distance. And Y is taken as delta here, and delta is nothing but only the boundary layer thickness. So you have to find out delta star by theta. This type of questions is very important, and we have to know how to solve this type of problem. Basically, the distribution pattern is given as U by capital U equal to Y by delta, and we have to know how to solve this question. Then, first of all, you have to use the formula, that is delta star equal to integration of U to delta 1 minus U by U infinity, or you can say the capital U into dy. So first of all, you have to putting the value of U by capital U here, then you can get that is U by capital U value you can take. It is Y by delta. So Y by delta is putting here, and now you have to integrate integration of 1 with respect to Y, that is what dy integration of 1 with respect to dy is Y, and integration of Y by delta. So Y is variable and delta is constant. So Y integration of Y is called is here Y square by 2. So the integration is all have to know how to solve or how to calculate the integration questions. Basically, integration is taught in the student for the student in class 12. This is the basic thing, and you have to know what is the formula, and you can easily solve the question. What is the momentum thickness? Momentum thickness. How to calculate the formula is integration of u by u to delta and u by capital U 1 minus u by capital U into dy. Okay, so we can putting the value of U by capital U, that is a velocity distribution, that is Y by delta. Formula is theta equal to 0 to delta Y by delta 1 minus Y by delta into dy. Basically, you have to put the value of U by capital U, and after that you have to integrate the values. Then Y by delta integration Y square by 2 delta, and Y square by delta square integration you can get, that is Y cube by 3 delta square. Then finally you can solve what is the value of theta. It can obtain delta by 6. If we find out the delta double star, then we have to use the formula of delta double star, that is energy thickness. It is found to be 0 to delta integration and U by capital U into 1 minus U square by capital U square into dy. So here also we can put the value of U by capital U here, that is the velocity distribution profile equation, and we can easily solve the integration. So we can get delta star value. It is found to be delta by 4. So in the fourth part, we have to solve what is the ratio delta star to the theta. So we have to put delta star value, that is different thickness value is delta by 2, and momentum thickness value is delta by 6. By putting these two values, we can get what is the value of this ratio. Now problem 13.2, we have next question, how to solve the question. So here we have to find out the distribution thickness. So in this case, the distribution thickness we can calculate. We have to know what is the velocity distribution pattern. So in this case, the velocity distribution pattern is given as U by capital U equal to 2 times of Y by delta minus Y by delta square. Basically, the distribution u by u infinity, or you can say that u by capital U is equal to 2 times y by delta and minus y by delta square is given that. So in this case, also we have to find out the delta star. So to find out the delta star or the resultant thickness, the formula is u integration of u 0 to delta 1 minus u by u in infinity, or you can say that u by capital U here. So we have to put the value of u by capital U here. So by putting the value, we can check and integrate the values given. Then delta star can be find out by solving. We can get the multiply and by squaring a minus b whole square formula you can apply, or you can simply solve this equation. Then you can get what is the value of delta star. The thickness is found to be one third of the thickness, that is delta. Modular thickness. Now, the momentum thickness you can find out by the formula of u delta, u by u infinity, or you can say that u by capital U, 1 minus capital U by capital U. This is the formula given for the moment. Find out the momentum thickness for the particular question. Basically, in this question, we have to put the value of u by u, capital U. So this is given as the value, and we have to multiply and solve. After that, we have to do integration. Then we can find out what is the value of delta. That is what is the value of theta. Theta is nothing but on the momentum thickness. So we can get easily what is the value. Now next is how to find out the energy thickness based on the question given, that is the energy thickness. In this case, we have to find out what is the value of U by capital U ratio, or you can say that velocity distribution pattern value. So in this case, we have putting the value of U by U infinity, and then by the solution of a particular question, we can get what is the value of energy thickness. So we can simply solve these questions by a simple method, and we can get the energy thickness value is found to be 22 by 105 into delta. So this is the problem related to the momentum thickness, energy thickness, and distribution thickness. So this is the basic concept of solving the numerical problem. Now we will put the next topic, that is drag force on the plate, and how to find out the drag force on the plate in terms of the boundary layer thickness. Basically, for finding the drag force or to calculate the drag force, we have to uh, simple taking a plate. So this is the solid plate, and in this plate we have to take two sections. The one section is AD and other section is BC. And if we flowing liquid on this plate, then we can get the flow pattern, that is called boundary layer. And if we check the sections available between these two lines, that is AD and CB. AD and CB pattern is shown here, and in this case we have to formalize what is the initial distance. Delta X shows the distance between A and B, and tau naught is the wall shear stress available. So this is the basic diagram, shows the drag force. So suppose we have to consider the flow of fluid having the free stream velocity that is equal to capital U here, and over a thin plate. Okay, in this figure number 13.4, we have seen a diagram in which the location of the force or the drag force on the plate we can determine. If the velocity profile near the plate is known, then a small distance del x we have to know, and after that we have finding the delta x value. We can easily put the in the equation that is known as tau naught equal to mu du over dy at a distance of y equal to 0. dy du upon dy is nothing but only the velocity gradient at a distance of y equal to 0. And here we also find out the drag force or the shear force on the small distance, that is del x. Now the delta fd, that is drag force at a distance of delta x, is equal to shear stress into area. Basically, we have to know what is the basic formula of stress. Stress is equal to load per unit area. And here, if we find out the drag force, we can easily cross multiply that. And delta fd is found out the shear stress multiplied by area. Tau naught is the wall shear stress, and delta x is the distance between two sections, and b is the thickness of the plate. or you can say that the here B is taking the width of the plate here. And if we formalize the basic equation, then let's suppose u is the velocity at a point within the boundary and B is the width of the plate here. So we have to calculate the basic, that is mass flow rate entering into the side AB. What is the mass flow rate entering into the side AB can be calculated by using the integration of rho, that is density, velocity, and area of the strip at a distance dy. So this formula is used for calculating of mass flow rate. Rho is the density of the fluid, and here fluid is the water, and density is 10 to the power 3 kilogram per meter cube. By the formula of B into dy, we can calculate the area of the strip. Then basic equation we can find, and the mass rate of flow leaving the side BC we can calculate easily, which is equal to mass through the AD plus change in mass flow rate at a distance dy. So we can calculate mass flow rate through the section AD is calculated with the formula of integration of 0 delta rho u b dy, and change we can calculate delta by delta x of this initial mass flow rate. Now we have to apply the steady state conditions. Then mass rate of the flow entering to the AB plus mass rate of flow entering to the DC can be easily summarized, which is equal to the mass rate of the flow leaving the section BC. Mass of the rate of flow entering to the DC is basically can be calculated with the formula of mass rate of the flow through the BC minus mass rate of the flow through the section AD. So by this formula, we can calculate, this formula is nothing but only delta by delta. Delta upon delta x within bracket 0 to delta rho u b dy into del x. Del x is the distance between the two sections that is already defined previously. Now momentum flux entering through the AD can be calculated with the formula of 0 to delta integration momentum flux per unit strip or the thickness dy, and which is equal to the mass through the strip into velocity. Basically, mass flow rate we have calculated the formula rho u b dy into velocity is u. So final formula is integration of 0 to delta rho u square b dy. Now momentum flux we have to find out the leaving the section BC. Then this equation is formed, and this equation 0 to delta rho u square b dy plus delta by delta x integration of 0 to delta rho u square b dy is the formula available here. And now we have to check what is the amount of flux entering into the side BC. So this is also calculated with the previous method, then mass flow rate entering through the DC into velocity. So this equation now forms, that is delta by delta x 0 to delta rho u capital U b dy. Capital U is the free stream velocity and delta x is the distance between the two sections taken previously. Now we have to check what is the rate of change of momentum by this control volume, and this can be calculated with the formula momentum flux through the BC minus momentum flux through the AD minus momentum flux through the DC. So we have put the values here, momentum flux through BC and the momentum flux through AD, and after that momentum flux through DC. Then all values are when we putting, then we can get the final formula, that is called, that is rho b del upon del x, and the 0 to delta u square minus u capital U dy into del x. Here u is the local velocity and capital U is the free stream velocity, delta is the boundary layer thickness, and u rho is the density of the fluid, b is the width of the plate. Basically, if the plate is a flat plate, then del p upon del x should be equal to 0, and it means that there is no external pressure force acting on the control volume. Now we have to find out the FD. Then F delta FD is the drag force, is equal to tau naught delta x into B. Total external force acting in the direction of the change in momentum. Then we can use the formula tau naught delta x into B with negative sign. In this case, by using the momentum principle, we can equate two equations 13.9 and 13.8. Then this is the equation in left hand side is 13.9 and equation right hand side is 13.8. we can equate this formula and cancelling delta x into b on both sides and simplify this equation, then we can easily get the what is the final formula. The final formula is obtained, that is known as von Karman's momentum integral equation. This momentum integral equation is tau naught upon rho u square delta theta upon delta x. So you can easily calculate this von Karman's equation. This is very important for engineering students of B.Tech third sem. So at the last, we can say that you have to know how to solve von Karman's equations based on the shear stress. Sorry. Okay, we can now some, that lecture is over, and we will meet in the next lecture. Thank you.